Good afternoon, students. Let us start the lab class. In the previous lab class, we were discussing the RC coupled amplifiers conduction. And I had come up to the point of plotting the frequency response of the amplifier along with the tabulation of gain measurements. And I had stopped there. So impedance measurement was left out in the previous lab session. We are going to cover that now, and later on we are going to cover the amplifier circuit along with the JFET. So we had seen how to measure the gain and how to measure the bandwidth. For each value of the input frequency, you have to measure the output voltage, and you'll have to find out V0 by Vi. Then 20 log of V0 by Vi is the voltage gain in decibels. And you will be plotting this in a semi-log sheet with x-axis as frequency and y-axis as gain. And you will obtain a frequency response curve for the given amplifier. There you will mark 2 points on the curve at the minus 3 dB points, which we respectively call as FL and FH. And FH minus FL will give you the bandwidth of the amplifier. Now the last part of that experiment is to measure the input impedance as well as the output impedance. Let me briefly write a picture here of an amplifier. So this is going to be an amplifier where we can have something called Zi and we can have something called Z0 here, where this is a junction. I hope let me clear this and let me write a bigger picture. Let me write in a different color. Okay. So now this is Zi, we can also write it as Ri because we are measuring in ohms, and this is Z0. Whereas this here it will be Vi and then here it is V0. So you can visualize the complete transistor amplifier circuit with this particular symbol. Can anybody tell me why the amplifier symbol is like this as a triangle? You can unmute and tell me, or you can put the answer in the chat box. Can anybody tell me why the amplifier symbol is a triangle? In general, we write the amplifier symbol in this way. Why we write the amplifier symbol in this way? Can anybody tell? There are 15 students in the lab now. Okay, as no one is telling, ultimately I am only going to tell. So, amplifier is supposed to have a very high input impedance and very low output impedance. Ideally, any amplifier should have infinite input impedance and zero output impedance. That is what is indicated by this symbol of triangle. When a signal comes from this side, there is a wall here, as if the signal is seeing a big wall here. That indicates very high input impedance. And finally, the wall converges into a point. And here you can see when the signal is coming out, it is easily going out. There is no wall at the output side. At the input side, there is a wall, and output side, there is a point, which simply indicates Zi is infinity and Z0 is 0. For that purpose only, amplifier is given this particular symbol, and the same symbol is used for a buffer as well in the digital logic circuits. Now, for the digital logic circuit, when the buffer is there, we put a bubble there in the digital domain and we call it as an inverter. What is basically an inverter? Inverter is also an amplifier only. The only thing is inverter will go into a two states, either 0 state or 1 state, based on whether the switch inside is completely off or completely on. Otherwise, inside the inverter also, it is a transistor only. When it is used in the cutoff region and in the saturation region, then we use it in the digital circuits, in the logic gates. When this transistor is used in the active region, in the middle of the load line, then we use it as an amplifier. Otherwise, the symbol for amplifier and the symbol for buffer are one and the same. Why we put a bubble there for the inverter is to indicate that there is a logic inversion. You give 0, output is 1. You give 1, output is 0. For that purpose only, that bubble is given. So now, when you understand that the symbol of the amplifier is a big triangle, look at this triangle. Inside the triangle, we have one input impedance. As soon as the signal is coming in, it is seeing an impedance. Ideally, input impedance has to be very high, but practically the input impedance will be there as few kilo ohms or few mega ohms. That is indicated as a resistor which is connected to ground, because as soon as a signal comes in, it is seeing this resistance with respect to ground. That is why it is written this way. Otherwise, Zi is not physically present inside the amplifier. You have already studied the AC analysis of the amplifier circuits, so you know how to compute the impedances of amplifier circuit. So here when Zi is shown this way, how to show Z0 now? Zi is shown in parallel because when the signal enters into the amplifier, it is actually seeing a large resistance with respect to ground. Now internally the signal will get amplified. That I have not shown here. Anyhow, the triangle symbol itself is an amplifier. When the signal gets amplified, it has to gradually pass into the output. At the output, what will be there? At the output, there will be a load. We can signify the load again as one more resistor connected to ground. And we can call it as RL now. That load can be anything. The load can be a light, load can be a speaker, it can be anything. Or the load can be one more amplifier at the next stage also. Now, how to indicate output impedance? Input impedance we have shown as if it is with respect to ground. But why are we showing output impedance in series? Because of the output impedance, there will be some loss here across Z0. Otherwise, ideally, output impedance is supposed to be 0. Means all the amplified output is supposed to appear across RL. But because of the output impedance of the amplifier, all the output that is amplified will not appear across RL. Part of that will be lost or dropped across the amplifier itself. So that is why output impedance is shown in series with the load, whereas input impedance is shown in parallel with the input itself. So in this way, when you visualize, you please understand that Zi and Z0 are physically not present inside the amplifier. They are part of the complete circuitry. Now it is not a static value which can be measured. Now it is a dynamic value. How to measure the input impedance and output impedance now for an amplifier is the question. So what we do in the lab is now, unlike the AC analysis, in the AC analysis, we do a mathematical model of the transistor and then we compute the impedances. But in the lab, we have to practically measure the input impedance and output impedance. So what we do is going to be told to you now. You can see this procedure where a single stage RC coupled amplifier circuit is connected and one decayed resistance box or a potentiometer is connected in series with the input. Now let me completely stop this annotation. Let me start a new annotation. So I will write Zi like this. And I will write Z0 like this. Okay, now this is Z0, this is Zi. Now we have this complete circuit here. This complete amplifier circuit is rigged up using a transistor and the associated resistors and capacitors. Now to this input we connect one decayed resistance box. It is called as decayed resistance box because this box contains some knobs, 6 to 8 knobs. Each knob contains 10 values like 1 ohm, 2 ohm, 3 ohm, 4 ohm up to 10 ohm. Next knob will contain 10 ohms, 20 ohms, 30 ohms, 40 ohms like that. Next knob will contain 100 ohm, 200 ohm, 300 ohm like that. It goes on like that. That is why I told you this box will contain 6 to 8 knobs. Now we can fix up a value of this resistance using this decayed resistance box. It is called as decayed because each knob contains 10 values. Now what we do here is, we have this decayed resistance box, which is a variable resistance. We can indicate using a potentiometer symbol also. Now we connect this input voltage, connect as given in figure with the DRB resistance 0, adjust the input V into 30 millivolts, let the frequency of the input be around V0 maximum. That means wherever you got the gain as maximum, you fix up the frequency of the input signal for that particular value. Now note down the peak-to-peak amplitude of the corresponding output V0. For example, let us say input is now 30 millivolt. Let us say input is 30 millivolts. Let us say at 100 kilohertz. Let us assume that at 100 kilohertz the gain is maximum or it is actually flat. From FL till FH above, in between FL and FH, gain will be flat. It will be constant. So let us assume that it is 30 millivolts and 100 kilohertz. Let us assume that the output is now, let us say 6 volts. 6 volts peak to peak. Let us say the output is now 6 volts peak to peak. Now what we do? Increase the resistance included in the DRB and observe the magnitude of the output V0 simultaneously on the oscilloscope. When the magnitude of the output V0 is reduced to half of its original value, stop varying the resistance further and remove the potentiometer from the circuit. Then V0 is VA by 2. Measure the value of the DRB and this measured value will be the input impedance. Which means you keep on increasing the resistance in this decayed resistance box by turning the knob. And you keep on observing the output in the oscilloscope, and whenever the output becomes 6 volts peak to peak by 2, that means when the output becomes 3 volts peak to peak, at that time you stop there and you measure the value of the decayed resistance box. The value of the decayed resistance box itself indicates the input impedance of the amplifier. Now can anyone tell me what is the logic behind this? Actually, we are connecting an external decayed resistance box to the amplifier and we keep on increasing the resistance until the output drops to 50%. Then we take that value as the input impedance of the amplifier, whereas input impedance is actually inside the amplifier. It's a dynamic quantity which cannot be directly measured. But how did we measure it this way? How did we come to a conclusion that when the output voltage becomes half, then the value of the decayed resistance box itself is input impedance? Can anybody answer this question? Students are all awake, right? No one is putting an effort to answer.
Is it because they can?
Is it because of? Can you be clearer? I could not hear you properly.
They're connected in parallel, sir.
They are not connected in parallel. They are connected in series, no?
Oh.
If you see, DRB is connected in series with ZI. Anyway, Rohit tried to give the answer. Can anybody else make an effort? Okay, I'll tell you the answer. The answer is, when this DRB value is kept on increasing, let us say around 1.5 kilo ohms. I'm just giving a crude example. Let us say around 1.5 kilo ohms, when the decayed resistance box value is there, at that time, let us say the output is dropping to 3 volts peak to peak. Then we take this ZI as 1.5K itself. Why? You can look at this. 1.5K is connected in series with ZI, and we are measuring the output, which means we have been giving this 30 millivolts input here, and the 30 millivolts became 15 millivolts here, right? That is the logic here. So when this ZI and this 1.5K, let us say ZI and DRB both are equal, then it is working like a voltage divider network, right? When it is working like a voltage divider network, if the input is 30 millivolts, at the input of the amplifier, it will be 15 millivolts because these two resistance are equal. When the input is 15 millivolts, the gain of the amplifier remains the same. So earlier, when it was 6 volts peak to peak, when the DRB was having a zero resistance, complete 30 millivolts was available at the input. We were getting 6 volts peak to peak. When the input becomes 15 millivolts, automatically the output also becomes half of it. So that is the logic. Logic is DRB along with ZI are working like a voltage divider network. And when the DRB's value equals the value of the ZI, then actually there will be 50% drop across DRB of the input voltage itself. That 50% input voltage itself is getting amplified. So naturally you will get 50% of the maximum output. That is the logic. I hope you understood this. Why we are going for this procedure is because we cannot directly measure the input impedance by using a multimeter. If you connect a multimeter and connect it across this input and ground, and if you think that you can measure the impedance, it is not possible that way because the amplifier is biased with the DC voltage. It is an active device working inside. So it is not possible to actually measure because it is not a static resistance there. It is not like a physical resistance. That is why we have to go for this particular approach. So that is the method for finding out input impedance. Now looking at this picture, can anybody tell me what is the logic behind finding the output impedance? Measuring of the output impedance is reverse of the input impedance. Let me write the output impedance now. See, the output impedance is like this. This is now Z0. Earlier, when we measured input impedance, we connected DRB in series here along with the ZI. Now Z0 is in series and we are connecting DRB in parallel. So here what happens now? We follow the same procedure. Connect as given in the figure with the DRB. Now the DRB resistance is maximum. You can see here. In the earlier case, DRB we kept it at 0 in the beginning. Later on we kept on increasing, because in the beginning we wanted the maximum output for the given input. Now why are we keeping DRB maximum? Can anybody tell me? Why are we keeping DRB maximum now? What will happen if we keep DRB minimum?
To get minimum output, sir.
Not that way. Not exactly for the minimum output. Output we want the same output. Earlier if we had 6 volts peak to peak, now also we want 6 volts peak to peak only. And we are going to reduce it to 3 volts only now also. because this also is working like a voltage divider network only. We have to keep this DRB resistance maximum. Otherwise, you cannot keep it minimum here. You cannot keep it 0. If you make it 0, what is happening? Output is getting shorted to ground and the transistor may fail. The whole circuit may burn out also because you are connecting the output to ground. That should not be done at all. That is why DRB resistance is kept maximum. Now, once the DRB resistance is kept maximum, we have this dynamic Z0 inside. We have this Z0 dynamic quantity inside. Now what we do is, initially we have 6 volts here now, output, as an example. Now we keep on reducing this DRB from the maximum value to some particular value. And we note down at what particular value, again the output becomes 6 volts divided by 2. Why? You look at this, when DRB was maximum, at that time, whatever was the output of the amplifier, that is coming out. So let us say here it was 6 volts at the amplifier's output that was passing through Z0 and it was coming out. But at that time, we were connecting an oscilloscope here. So current output is very less there because we are connecting an oscilloscope. So even though Z0 is there, across Z0, there will be no voltage drop, because we have not connected any load at the output. We have kept DRB maximum or maybe infinity, let us say. In that case, there will not be any drop across Z0 because current is very less. Now we keep on reducing DRB. Imagine we reduce DRB to a value of, let us say, 2K. I am giving an example of 2K. Let us say to a value of 2K. When we give a value of 2K, let us say the output drops to 6 volts peak to peak by 2, that is 3 volts. Now again this Z0 and DRB are working like a voltage divider network. Now when this 2K is equivalent to the Z0, what happens is there will be 3 volts across this Z0, 3 volts across this 2K. So it is working again like a voltage divider network. So the value of DRB at which the output drops to 3 volts, that itself is now taken as Z0. So you should take care when you conduct experiment in the lab, you should take care that whenever you measure output impedance, you should keep the DRB at the maximum value only. Otherwise, if you keep it at minimum, let us say 0, now the Z0 gets shorted to ground and more current will flow through Z0 to ground and transistor may burn out also. That safety precaution you should take when you conduct the experiment. As far as for input impedance is concerned, such precaution is not necessary because input impedance we are connecting in series, whereas for output impedance we are connecting DRB in the parallel. So we should be careful at that time. So this is the procedure for measuring input impedance as well as output impedance. And with this, I am ending this particular RC coupled amplifiers experiment. I will be going on to GFET experiment. Meanwhile, if you have any questions, you can ask me.
Sir, I'll post the attendance link, sir.
Yeah, you can post.
Once I have posted the attendance link, you can enter the attendance meanwhile.
Okay, Prithviraj sir has posted the attendance link in the chat box. You can click on that, you can enter your attendance also. So I'll start with the FVT experiment. The aim is to determine the gain, frequency response, input and output impedances of a FET RC coupled single stage amplifier. Now, in the BJT experiment, we used one transistor called SL100. In the FET, we are using one particular transistor called BFW10. In general, when they started manufacturing transistors, they used to give different type numbers. For germanium transistors, they used to give a type number starting with A, and for silicon transistors, they used to give a type number starting with B. That is how we have transistors starting with AC127, BC547. So different numbers are there. So here FET, it is starting with B, which indicates it is a silicon transistor. And later on, they will have different alphabets like F and W. They don't have any specific meaning as such. Just like in our vehicles, for bikes or cars, we have a registration number where only that KA stands for Karnataka. Later on, there will be some other number for a particular RTO office or a particular zone. And later on, we will have some other numbers, which is alphanumeric. And they don't have any abbreviations or they are not expansions. Same way, even for devices, active devices, they used to give all these numbers. The European system was to give alphabetical numbers, and the American system was to give numerical numbers. Always, Americans wanted to be different from the Europeans. So that way, as Europeans had a right-hand drive, Americans started a left-hand drive. As Europeans started using 220 volts, Americans started using 110 volts. That way, there are so many such differences. Similarly, when Europeans started giving type numbers as alphabets, starting with A and B, Americans started giving numbers with 1N and 2N. 1N for diodes and 2N for transistors. That way, we have 2N5551 as a transistor, 2N5401 as a transistor, 1N4007 as a diode. So that way, they used to give numbers. Anyhow, in India, we are using all American as well as European products. We have both type numbers in India. So, this FET which we are going to use is called BFW10. And along with that, we will have resistors, capacitors, power supply, signal generator, CRO, DRB, and the springboard. Now, this is the circuit diagram. Let me slightly zoom. Okay, you can see the circuit diagram now. We are using an FET called BFW10. And even for FET also, we are going to go for voltage divider bias only. Anyhow, in the theory class, we have already studied about the voltage divider bias network. So now R1 is 1 mega ohms, R2 is 33 kilo ohms, and RD is 1.5 kilo ohms, and RS is 1 kilo ohms. Along with that, we have a DC blocking capacitor 0.1 microfarad and coupling capacitor 0.1 microfarad. Then we have a bypass capacitor is 100 microfarad. I had told you already that the bypass capacitor has to be of much larger value because we don't want the Q point to be disturbed. We want the source voltage to be pure DC. For that reason, we use a large value bypass capacitor. Now you can see the diagram of this transistor BFW10 where you have a key here in the middle. Wherever there is a key, adjacent to that, you will have to keep this BFW10 facing towards you, means it is upside down. All these pins will be at the bottom side of the transistor. You will have to be seeing the bottom side of the transistor only. So at the bottom itself, this key is available. When you are seeing this key upwards, left side is substrate, right side is source, and bottom side is drain, again left side is gate. For the time being, you can completely ignore this substrate. The substrate need not be connected to anything because we are conducting a discrete experiment now. When you come to third year, you will study more about MOSFET construction, JFET construction. There you will understand what is the exact usage of the substrate. Substrate basically means the wafer itself or the base on top of which transistor is manufactured. For example, when you are consuming a pizza, you will have a pizza base. Above pizza base, you will have a cheesy cream, and then later on you will have toppings. Same way, that pizza base is utilized as an edible material above which you will have toppings. In the same fashion, whenever we have to manufacture a transistor, we need a base on top of which we will do doping. Doping of either arsenic or phosphorus or boron. Boron is for P-type, arsenic or phosphorus for N-type. So when you perform doping, below which there is a base material of silicon, that is called as substrate. It is also called as the body of the transistor. But as such, we are not using the body for any of our purposes here because we are using a single transistor. If at all we have multiple transistors on an integrated circuit, then even the substrate cannot be left open because it can pick up noise from atmosphere. But here where we are using a discrete JFET, so we can simply leave the substrate open also, or if you want, you can connect it to ground also. There is no issue. Even if you connect it to ground also, it is fine. Even if you leave it open also, it does not have so much of sensitivity because we are using it as a discrete device. And moreover, we are giving input in millivolts only. So even if the atmospheric noise is present outside, atmospheric noise will be in either microvolt or nanovolt, it will not affect us much here. So substrate terminal can be left open or it can be connected to ground also. Later on, you already know, to the gate we have input terminal, to the source we have this RS connected, and to the drain we have this RD connected. Then we have the capacitors being connected, and we switch on the power supply. Now, as soon as we switch on the power supply, before giving the input signal, you should measure the DC voltage at the drain. It should be approximately VDD by 2. That means here VDD is 10 volts. At the drain, approximately the DC voltage must be half, about 5 volts. Actually, it will be 5 volts plus, let us say, around 1 volt. It will be around 6 volts here because we have source resistance also here. If the transistor is exactly in the middle of the active region, then across the transistor you will have half the supply voltage. The remaining supply voltage will be across RD and RS. So somewhere around 5 to 6 volts is the DC voltage that you should check at the drain. If you are not getting that, then you'll have to switch off the power supply and you have to check the connections once again. Somewhere some connections may be missing, or somewhere you might have put a wrong value of a resistance itself. You already know the color code of the resistors now. You should be carefully observing the colors of these resistors and accordingly you should connect them. And even this 100 microfarad has got its own polarity. 100 microfarad is going to be an electrolytic capacitor. So it has got a plus and minus. Plus should be always connected to the top and minus should be connected to the ground. Otherwise, if you reverse this capacitor, there are chances that internally it will heat up because it has got electrolyte inside. So because of the reverse electrolysis action, there may be gases being produced inside the capacitor, and gradually capacitor may bulge, or sometimes capacitor may simply explode like a pataka also. So you should be careful. Of course, it is not really very dangerous because the value is only 100 microfarad. So it is not really very dangerous. But you should be careful that if at all it explodes on your face only, you may have burns or wounds also. That's why whenever you use electrolytic capacitors, always remember electrolytic capacitors will have their polarity because inside the capacitors there is electrolyte. Always the minus plate should be connected to ground, plus plate should be connected to the top. Whereas these two capacitors are ceramic capacitors. The 0.1 microfarad indicates that they are less than a microfarad, or 0.1 microfarad, we can also tell it as 100 nanofarad. They are not electrolytic capacitors, they are ceramic capacitors, they don't have a polarity as such. Now I should tell you one more thing. Sometimes in the ceramic capacitors, there will be a number written like this. It is like 104. In case of resistors, there will be a color code. Whereas in case of capacitors, they will print some number. This 104 indicates 10 followed by 4 zeros. So the last 4 is a multiplier. 104 means 10 followed by 4 zeros. You should actually take it as picofarad now, because the unity is now picofarad. This simply indicates 100,000 picofarad or 100 kilo picofarad. 100,000 picofarad is 100 kilo picofarad. Now 100 kilo pico is nothing but 100 nano. Kilo into pico. Kilo is 10 power 3, pico is 10 power minus 12. This is nothing but 100 nanofarad. 100 nanofarad is nothing but 0.1 microfarad. That is what is this? 100 nanofarad is nothing but 0.1 microfarad. So some manufacturers directly put a number 0.1 on the body of the capacitor. Some other manufacturers simply put a number like this. They put a number like 104. Similarly, if it is 103, then you should understand that is 10 followed by 3 zeros, that is 0.01 microfarad or 10 nanofarad. If it is 102, then it is 10 followed by 2 zeros. It is nothing but 1 nanofarad, 1000 picofarad or 1 nanofarad. If it is simply kept as 101, then you should take it as 100 picofarad. 10 followed by 10, that is 100 picofarad. Sometimes if it is 100, what does it mean? If it is 100, what does it mean? Anybody can answer?
10 picofarad.
Exact. It is 10 picofarad. If it is 100, then it is 10 picofarad, which simply indicates that it is only 10 and there is no further 0. The last multiplier is 0, which indicates it's a 10 picofarad. So this is how manufacturers give different numbers on the body of the capacitor. The reason is capacitors will be very small. There will not be any space left on the capacitor's body to print the color codes. Resistor is a elongated material, lengthy material, whereas capacitor is a round cap. Inside that there will be 2 plates, circular plates. So that way, on the capacitor, there will not be any enough space to print the color codes. It is better that they use such numbers. So you should remember all these things. You should identify these things in the lab. Now, apart from that, the procedure for conducting the experiment is the same as the BJT. That means you give an input voltage. Right now here you are giving input voltage more. Can anybody tell me why we are giving 500 millivolts here? Whereas in BJT's experiment, we gave 30 millivolts. Can anybody tell me why? Okay, the reason is BJT amplifier will have a larger voltage gain, whereas FVT will not give a larger voltage gain. We had done those exercises in the theory classes. The FVT amplifier will give hardly 3 times, 4 times, 5 times voltage gain, whereas BJT amplifier will give 150 times, 200 times voltage gain. That is why in the BJT experiment, we gave 30 millivolts. Here we are giving much larger input voltage, around 500 millivolts, because we know that the gain will be hardly 3 times, 4 times or 5 times. If you give 500 millivolts, if the gain is 5, you may get around 2500 millivolts or 2.5 volts. That is the output amplitude which you are going to get. So, give the power supply plus 10 volts. First check whether the FET is in the active region by checking the DC value here in the drain. It should be in between 5 volts to 6 volts. Otherwise, you check your connections, check the values of the resistors also. And if you are getting the DC voltage, then it indicates, if it is in between 5 to 6 volts, it indicates that the transistor is half on. Then you can connect the signal generator and you can conduct the experiment by gradually increasing the frequency from 0, and you can keep on measuring the gain and keep on calculating the voltage gain for a given frequency. Later on, the procedure is same. You will have a tabular column. As per the tabular column, you will tabulate the gain and the frequency. You will plot the frequency response of this amplifier using a similar graph sheet. And even for measuring the input impedance and output impedance also, the procedure is same. you are going to connect a DRB at the input in series for measuring input impedance, and you are going to connect the DRB in parallel at the output by keeping it maximum for measuring output impedance. So all other things are one and the same. Let me discuss the design now. So VD, there are these typo mistakes here in this manual. You just ignore this typo mistake as of now. Our output voltage has to be VDD by 2 or 5 volts. Let us choose a drain current as 2 milliampere. Now for BFW10, IDSS is 10 milliampere and VP is minus 3 volts. You already know about this, right? Saturation current for BFW10 is 10 milliampere and pinch off voltage is minus 3 volts. We already know this Shockley's equation. Shockley's equation is ID equals IDSS into 1 minus VGS by VP whole squared. So we can substitute the IDSS that is given for the FVT 10 milliampere and the pinch off voltage given for the FVT is 3 volts. And we have chosen the drain current to be 2 milliampere. So 2 milliampere equals 10 milliampere into 1 minus VGS by minus 3 whole squared. So solving this, we get the value VGS has to be around minus 1.68 volts. Now we know that ID is there. So naturally, again, there's a typo mistake here. This has to be that RG. It is not VGS. It has to be resistance. Resistance is voltage by current now. So it is VGS by ID. So that is 1.68 volts by 2 milliampere. That is going to be 1 kilo ohms. That is what is this RS here now. This RS we obtained as 1 kilo ohms. Now after obtaining this RS as 1 kilo ohms, we can apply KVL to the output side. RD plus RS into 2 milliampere plus 5. This 5 is nothing but VDD by 2, which is across the FET. We have total voltage is 10 volts. Now we already have the value of RS. By using that, we can find out the drain resistance RD, that we get around 1.5 kilo ohms. So the drain resistance is now 1.5 kilo ohms and the source resistance is now 1 kilo ohms. The source resistance we found out using Shockley's equation. Actually, using Shockley's equation, we found out VGS, and by using that VGS, we found out value of RS. Now, applying the KVL at the input side, VG is VGS plus VRS, that is VDD divided by R1 plus R2 into R2, because R1 and R2 together are the voltage divider network there. So substituting all those values here now, 1.68 into 2 milli into 1K is 10 into R2 by R1 plus R2, or we get R2 by R1 plus R2 equals 0.032. Now we can expand it as R2 as 0.032 R1 plus 0.032 R2. We can choose a respective value of R1. R2 by R1 is 0.032. Now choosing R1 as 1 mega ohms, again there's a typo mistake here. So our earlier teachers who did this particular lab manual, they did not take much care, and now I should apologize on their part now. Anyway, I don't know who they are. Let us leave them for the time being. Choosing R1 equals 1 mega ohms, we can choose R2 equals 33 kilo ohms. Now we have R1 1 mega ohm, R2 33 kilo ohm, R1 1 mega ohm, R2 33 kilo ohm, RD 1.5 kilo ohms, RS is 1 kilo ohms. All these design aspects are already discussed in the theory class. So you don't have to worry much even if I go faster here. Now based on this, we have the circuit, and later on we can conduct the experiment. All other procedures, other things are similar to BJT amplifier, and all other procedures are the same as the BJT amplifier. So with this, we are ending this JFET experiments, JFET amplifiers experiment. In the next class, we will start with oscillators. Meanwhile, if you have any questions, you can ask us, or else we will wind up the class. Are there any questions, students? Okay, if there are no questions, let us wind up the class. Meanwhile, you can check our college website and you can go to EC department there and you can see the lab videos that are posted there and you can go through the lab videos also there. Prithviraj sir, shall we end the class now?
Yeah, around 5 absentees were there, sir. One joined very late.
Okay,
Yeah.
we will end the class now.
Yes, sir.
Okay, students, see you in the next class. I have recorded the session of this class also. I will be putting the Google Drive link into the Google class. You can go through the recording also. See you in the next class. Take care and goodbye.